Yeah, very good morning, everyone. Today we are going to discuss about conversion of quadratic equation to matrix form, and then matrix form, and that matrix form to diagonalized matrix, and after that diagonalized matrix to canonical form, and nature of the quadratic equation or eigen values or the matrix A. So this is what today we are going to discuss. So today we are going to discuss about quadratic equation to matrix form, then matrix form to diagonalized matrix, then diagonalized matrix to canonical form, and canonical form. After obtaining canonical form, we are going to find nature of the quadratic equation or nature of the eigenvalues or nature of the matrix A, nature of solutions of matrix A. That is what we are going to discuss in today's class. Okay, we want to study the nature of quadratic equation, or we want to study nature of the obtained matrix, or we want to study nature of eigenvalues in three different cases, and there is one special case using signature, index, and rank also. So today's class we are going to discuss only these three. So for this we want to write an equation. Our quadratic equation is 2x1 x2 plus 2x2 x3 plus 2x1 x3. Let this is our matrix. This is our quadratic equation. Now we want to convert this quadratic equation into matrix form. For this we are assuming matrix A. So matrix A is given by the combination of elements, that is combination of variables called x1, x2 and x3 in row and column wise. x1, x2 and x3. So how here we have to write means here when x1 is meeting, when x1 and x1 are appearing in element, then it will be called x1 square. If x1 and x2 are appearing, it will called x1 x2. When x1 and x3 are appearing, it is called x1 x3. So this is x1 square, that is always a11, then a22 and a33 will be the square elements. If suppose I am having here x1 square plus x2 square plus x3 square means here the square terms will appear, the coefficient of square terms will appear. How? Means here we are having coefficient, so coefficient of here coefficient of x1 square, here coefficient of x2 square, here coefficient of x3 square. So these three will be used in the position of diagonal elements, whereas in remaining position, that is here, what will come here, we will have a 1 2, here it is a 1 3, here it is a 2 1, and here it is a 2 3, here a 3 1, here a 3 2. So for these positions we want to have half into coefficient of corresponding elements, half into coefficient of, so half into coefficient of, so half into coefficient of x1 x2, here half into, I have no space to write coefficient, the word coefficient, so I am just putting half only, so half into coefficient of x1 x3, here half into coefficient of x2 x1, half into coefficient of x2 x1, here it is half into coefficient of x2 x3, here half into coefficient of x3 x1. Then here we will have half into coefficient of x3 x2, half into coefficient of x3 x2. So now the resultant matrix will look like A equal to see x1 square coefficients, x2 square coefficients and x3 square coefficient will be written in the same way, that is not divided by 2, whereas the remaining elements coefficients will be divided by 2. That is what this matrix shows. So coefficient of x1 square, x2 square, x3 square will be written as it is and or as they are, whereas the remaining elements will have the half of their coefficients in the corresponding positions. So we will have 1, then 1, here also 1, here also 1, here also 1, and here also 1. Okay, this is what our matrix resembles. This is what our matrix resembles. Okay, now this is a symmetric matrix, but I just shown this matrix to explain how to write the matrix, how to write the quadratic form into matrix form. But for today's problem we are not going to consider this. So we are having only 2x1 plus 2x2 plus 2x3 means then our diagonal elements will become 0, 0 and 0. These will be our diagonal elements. So now we have A. So for this A we want to write the characteristic equation. The characteristic equations for the 3 by 3 matrix or the matrix of order 3 can be given by lambda cube minus s1 lambda square minus plus s2 lambda minus s3 equal to 0. So here what is s1? So s1 means, I shall write here, s1 equal to sum of main diagonal elements, that is equal to 0, plus 0 plus 0, so that is equal to 0. So our s1 will become 0 plus, then what is s2? s2 is sum of the minors of main diagonal elements. So for the main diagonal element 0, we will have the minor 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. Plus for the second element we will have 0, 1, 1, 1. For the third element we will have 0, 1, 1, 0. So that is equal to 0 minus 1 is minus 1, then 0 minus 1 is minus 1, here also 0 minus 1 is minus 1, that is s2 equal to minus 3. So for s2 we will have minus 3 lambda. Then what will be s3? So s3 is determinant of A. S3 equal to determinant of A. So to find determinant of A, we can make use of calculator, and before that I shall explain how to find s2 in calculator. So to find s2 in calculator, First we shall find S3 and I shall explain how to find this S2 in calculator. First we shall fix matrix mode. So matrix mode is in 6. So I want to define matrix A. So we have taken matrix A in 3 by 3 dimension. So matrix is saying first element as 0, second element as 1, third element is also 1, then second row first element is 1, then the next element is 0 and next element is 1, the third row first element is 1, second element is also 1, the third element is 0. Now we have defined our matrix elements for the matrix A. Now we are pressing shift then 4, so after turning it on, shift 4, we can find determinant 7 of matrix A. Shift 4 matrix that is given in 3 matrix A. So determinant of matrix A is equal to 2. Determinant of matrix A equal to 2. So that is S3 equal to minus 2. Here it is lambda cube minus 0 lambda square minus t lambda minus 2 equal to 0. So we can verify this S2 once again using the formula. Instead of taking this minus, we can find adjoint A. We can find adjoint A. So adjoint A, the formula for adjoint A is, since A inverse is having the formula adjoint A divided by determinant A, this adjoint A can be given by the formula A inverse into determinant of A, okay, or determinant of A into A inverse. Since this is a scalar, we can write in the front. So determinant of A into A inverse, it can be written like that. So now we have for determinant A, and now we have to find determinant of A is 2. Now we want to find A inverse. So shift, so I turn it down, then shift 4, 3 is given in matrix A, matrix A inverse, matrix A inverse. Here I am writing shift 4, determinant is given in 7, so determinant of matrix A, so it is shift 4 is shift 4 3, that is matrix A into matrix A inverse. So determinant of matrix A into matrix A inverse. So we are having adjoint A as only diagonal elements are minus 1 and remaining elements are 1. Only diagonal elements are minus 1, all other elements are 1. So adjoint A can be given by minus 1, minus 1, minus 1 as the leading main diagonal elements, and the remaining elements are all equal to 1. 1 1 1 and 1. Now we are having adjoint A, so here we can find S2 by taking sum of main diagonal elements of adjoint A. For S1 we are taking sum of main diagonal elements of A, whereas for S2 we can make use of the formula sum of main diagonal elements of adjoint A. So S2 is given by -1 plus -1 plus -1, that is S2 equal to -3. So our S2 is correct, our S1 is also correct, and our S3 is also correct. Our characteristic equation is completely right. So we want to find the root for this characteristic equation. Lambda cube, either it may be plus or minus 0 lambda square minus 3 lambda minus 2 equal to 0. For this so here A equal to 1, it can be in the expressed as ax cube or a lambda cube plus b lambda square plus c lambda plus d equal to 0. So here a equal to 1, b equal to 0, comma c equal to -3, comma d equal to -2. So now we can use mode. What mode we can use? We can use equation mode. So in equation mode we want to use the fourth format. So the fourth format is having the degree. So a equal to 1, then b equal to 0, c equal to -3, and d equal to -2. So x1 equal to 2, x2 equal to -1. So we are having only two roots. We are having only two roots in this Casio calculator. Here in this calculator we can able to see the roots. X1 equal to 2, that is lambda 1 equal to 2, and lambda 2 equal to -1, So whenever you do the problem in Casio calculator and it shows only two roots for the cubic equation, means the second root is repeating. It shows actually the second root is repeating. So lambda 3 is also equal to minus 1. Number 3 is also equal to minus 1. Okay. So till this we have found the eigenvalues, because the roots of the characteristic equation are called the eigenvalues. Now we want to find eigenvectors. So this is our eigenvalues. Eigenvalues. And now we want to find eigenvectors. Want to find eigenvectors. So for this we want to consider A minus lambda I into x equal to 0, and we know what is our A. What is our A? The diagonal elements are only 0, so minus lambda, remaining elements are all 1, so here also minus lambda, it is 1, and here is also minus lambda, and here also 1 and 1. So A minus lambda I is this matrix is called A minus lambda I, and here x is given by x1, x2 and x3 equal to 0, 0 and 0. Okay. So if suppose we are having the equations in x, y, z, means we have to write, instead of x1, x2, x3 we want to write x, y, z. So we will have minus lambda x1, then plus x2 plus x3 equal to 0, and here x1 minus lambda x2, then plus x3 equal to 0, and after that x1 plus x2 minus lambda x3 equal to 0. So this is our equation, required equation. So we can take this equation as number 1 and this as our number 2 and this as our number 3. Okay, this is our number 3. So when we substitute lambda equal to 2, the above equation will become minus 2 x1 plus x2 plus x3 equal to 0. and after that we will have x1 minus 2x2 plus x3 equal to 0, and after that x1 plus x2 minus 2x3 equal to 0. Even though this is symmetric equation, here we are having two different symmetric matrix. Here we are having two different equations, so we want to find values for x1, x2, x3 by using cross multiplication. So it is x1, x2 and x3. Here we have 1 minus 2 and 1, and here next we are having minus 2 1 minus 2. I have taken these two equations. So from these two equations I am finding the cross multiplication. Okay, so we will have x1 divided by 1 plus 2 is 3 equal to x2 divided by 3, that is equal to x3 divided by 3. So the eigen vectors are 3, 3, 3. Since 3 is common for all the variables x1, x2, x3, we can simply write the eigenvector x1 yes. So x1 equal to x1, x2 and x3. For x1 we are writing 1 and 1 because we have taken 3 as the common factor for x1, x2 and x3. So in eigenvectors we can avoid such common factors, so we can simply write x1 equal to 1 and 1. Now for lambda equal to minus 1, so this equation is for lambda equal to 2. This equation is for lambda equal to 2. And now for lambda equal to minus 1, and it is also repeating 2 times, we can substitute only one time. So in lambda equal to minus 1, substitute here, we get 1x1 plus 1x2 plus 1x3, then 1x1 plus 1x2 plus 1x3, then 1x1 plus 1x2 plus 1x3. So in lambda equal to minus 1, we will get 3 equations, that is x1 plus x2 plus x3 3 times, which is equal to a single equation, that is 1x1 plus 1x2 plus 1x3 that is equal to 0. that is equal to 0. Here, since it is symmetric matrix and we want to do orthogonal transformation in order to make the eigenvectors x1 and x3 are pairwise orthogonal and x2 x3 are pairwise orthogonal. We have to form such kind of eigenvectors. If it is non-repeating eigen values, means definitely we will have pairwise orthogonal eigenvectors. But here, since the eigenvalues are repeating, they cannot be formed by themselves. We have to form it. So for that, we have to find two types of eigenvectors. First type is putting x1 equal to 0 in this equation, that is equation number 4. This equation, then we will get x2 equal to minus x3. x2 plus x3 equal to 0. So x2 equal to minus x3. So when x2 by x3 is written, we will have minus 1 by plus 1. x2 by x3 equal to minus 1 by 1. So which implies this is our second eigenvector, x2 equal to 0, then minus 1 and 1. So now we are having x1 and x2. So how to find x3? So x3 should be found by using pairwise orthogonal transformation. Using pairwise, P-A-I-R, pair wise pairwise orthogonal transformation. Pairwise orthogonal transformation. So how to find that? So for this we have to assume x3. So x3 can be assumed as L, M and N, and it is satisfying the condition, it will satisfy the condition x1 transpose x3 equal to 0. In the same way, x2 transpose x3 equal to 0. So it implies x1 transpose is 1 1 1 is 1 1 and 1 into L M N equal to 0, and for x2 transpose x3 we will have 0 minus 1 and 1. 0 minus 1 1 into L M N equal to 0. So now on multiplication we get L plus M plus N equal to 0, and after that 0 L plus minus 1 M plus 1 N equal to 0. Since these two equations are different, we can do cross multiplication again. L M N, it is 1 1 1 and 1, and again minus 1 1 0 minus 1. So the cross multiplication procedure. So we will get x3 equal to the values of Lmn. So 1 into 1 is 1, 1 minus 1 into 1 is minus 1, so 1 minus 1 is 2, so that is L by 2, that is I said right here also L by 2, and it is 1 into 0 0 0 minus 1 is minus 1, that is M by minus 1, that is equal to N divided by 1 into minus 1 is minus 1 0, so 2 minus 1 1, so 2 minus 1 minus 1. So this is our third eigenvector. So now we have three eigenvectors, and we have three eigenvalues, three eigenvectors. Now we want to find the normalized form and the normalized matrix. We want to find normalized form and normalized matrix. So what are eigenvalues? Eigenvalues are 2 minus 1 minus 1. So I shall write it here separately. The eigenvalues are lambda equal to 2, then lambda equal to minus 1, and again lambda equal to minus 1. The eigenvectors are x1 equal to 1 1 1, here x1 equal to 1 1 and 1, and x2 equal to 0 minus 1 1, 0 minus 1 1, and x3 equal to x3 equal to 2 minus 1 1 or minus 2 1 1. We can also write it as taking minus 1 commonly outside, we will get minus 2 1 1 also, minus 2 1 1 also. So I am writing it as minus 2 1 and 1 because to increase the number of positive terms. Okay, now so this is eigenvalue. For this eigenvalue we are having this eigenvector. Now we want to write the normalized form. Normalized form. Normalized form. So the normalized form is nothing but, so this 1 can be written in numerator 1 divided by square root of first element, that is 1 square plus 1 square second element plus 1 square. Second element is also the same. The second element is also the same, and the third element is also the same. For this x1, whereas for this x2 the normalized form is given by 0 divided by root of 0 square plus minus 1 the whole square plus 1 square. So this is so here we will have the second element minus 1 and the third element s, and third element s plus 1. S plus 1. So now we understand how to write this normalized form, and I hope definitely you don't want to so again how to write this in normalized form. You know that how to write this in normalized form, so I think I don't want to show it again. So now I am writing here itself. Yes, you had a very good understanding of this. So the normalized form is given by 1 divided by root 3, 1 divided by root 3, 1 divided by root 3 and 1 divided by root 3. and after that for x2 we want to find 0 divided by 2 root of 1 square plus 1 square minus 1 over square will become plus 1, so minus plus 1 plus 1 will become 2, so 0 by 2, that is 0 again, minus 1 by 2 and 1 divided by 2, and here we are taking, so 2 square is 4, minus 2 whole square is plus 4 plus 5 plus 6, so minus 2 by 6 means minus 1 by 3, we shall write it as minus 2 by 6 itself, minus 2 by 6, and here it is 1 by 6 and here it is 1 by 6. This is normalized form. Then what is normalized matrix? Normalized matrix. Normalized ZTD normalized matrix. The normalized matrix n can be given by the same vectors, normalized vectors, the same normalized vectors. Okay, see, I'm taking this okay, so place it here itself, and this and after that this. This okay, this is our normalized matrix. Now we want to find the diagonalized matrix. We want to find the diagonalized matrix, that is D, diagonalized matrix D. So the matrix capital D. So the formula for this capital D is n transpose A n, n transpose an. So what is n transpose? So n transpose is 1 by root 3, and here we will have 1 by root 3, and here also we will have 1 by root 3, and here we will have 0, then minus 1 by 2 and plus 1 by 2, and after that we can write minus 2 by 6 or minus 1 by 3, whatever it is. If you are feeling comfortable with minus 1 by 3, you can write minus 1 by 3, or else you can write minus 2 by 6 also, and it will not affect the result of the product of the matrix. So 1 by 6 and 1 by 6. Okay, so since I am feeling more comfortable with minus 2 by 6, writing it in the form of minus 2 by 6, I am writing as minus 2 by 6 because I want to see every denominators as the same. So minus 2 by 6. N transpose, what is A? A is 0, 1, 1, 1, 0, 1, then 1, 1, 0. N transpose A into N. So N is here, N transpose. So this is our N transpose AN. Now we want to write the value of D. We want to write the value of D. So what will be the product of multiplication of these three matrices? So when we multiply these three matrices, we will get the we will get only diagonalized elements. So there is a property in a triangular matrix, the eigenvalues can be taken from the diagonal elements of the triangular matrix. Okay, for any triangular matrix, the eigenvalues are nothing but the elements of the main diagonal elements of the triangular matrix. Okay, so that is what we are searching for here. Here we will have only diagonalized matrix. Diagonalized matrix means we will have only diagonalized elements, only diagonal elements only available. So all other elements will be 0. So all other elements will be 0. So all elements will be 0, and when only diagonal elements appear means this diagonal matrix is also be called as triangular matrix, because in the diagonal matrix can either an upper triangular matrix or lower triangular matrix. Okay, so for triangular matrix, the eigenvalues are nothing but the main diagonal elements. If we want to write the main diagonal elements for a triangular matrix, then what can be those main diagonal elements? It is nothing but the eigenvalues. So we can simply take the eigenvalues. So what are our eigenvalues? Our eigenvalues are lambda equal to 2, minus 1 and minus 1. Lambda equal to 2, minus 1 and minus 1. So we are having lambda equal to 2, then minus 1 and minus 1. So this is our D. D equal to 2, 0, 0, 0, minus 1, 0, 0, 0, minus 1. So now we want to write a canonical form. Now we want to write the canonical form. So for writing canonical form, I am making use of the place available here. For writing canonical form, canonical form means, again we are converting the diagonalized matrix into a quadratic equation. So for this we want to write y1 y2 and y3 into this d. So you can have the formula in mind: y1 y2 y3 in row into d into, and then y1 y2 y3 in columns. So 2 0 0 0 minus 1 0 and 0 0 minus 1 into y1 y2 y3. Okay, that is, we can simply mark and write 2y1 square. See, the result is 2y1 square minus y2 square plus minus y3 square minus y3 square. So this is our canonical form. Now we want to find the nature of the quadratic equation, that is nature of the matrix we have in matrix A. So we have in matrix A some elements. So we shall look into matrix A. In matrix A we are having 0 1 1 1 0 1 1 1 0. For this we have obtained the characteristic equation as lambda cube, then 0 lambda square minus 3 lambda minus 2. Since this characteristic equation is having both positive and negative terms, it is also having 0 also, but since it is having both positive 0 terms and negative terms, positive term, 0 term, negative term, or it can be simply said as it is having only positive and negative terms, it is called indefinite. The nature of the characteristic equation or nature of the matrix or nature of the quadratic equation is indefinite. So now we look into eigenvalues. So the eigenvalues are given by lambda equal to 2. It is a positive term. Lambda equal to minus 1. So since we are having both positive and negative terms, in eigenvalues, the matrix A is said to have the indefinite roots. The nature of roots are indefinite. The roots of the quadratic equations are indefinite. Okay, the quadratic equation is indefinite, whatever it is. Okay, the nature, the question is asked as nature, it is indefinite. Okay, the third thing is, now I have mentioned indefinite. What is indefinite and what is definite? So we will say positive definite when all the terms in the characteristic equation are only positive. We will say positive definite definite, DEFINITE, positive indefinite, negative definite, so negative definite means it is having the eigenvalues will have only negative terms. Okay, if you are having a 3 by 3 matrix and we are having 3 by 3 so 3 eigenvalues means, and all 3 eigenvalues are, if all 3 eigenvalues are negative, then it is called as negative definite. If all 3 eigenvalues are positive, then we can call it as positive definite. When we are having both positive and 0 means positive semi-definite, positive semi-definite, positive semi-definite. When we are having positive terms and 0 terms, at least 1 0 or 2 0, but it should be with positive term. And negative definite, the natural will be called as negative semi-definite, negative semi-definite. When we are having minus comma 0, so negative terms and 0 terms, it is also negative semi-definite. The final one is indefinite. So indefinite means when all the eigenvalues are considered, we can able to see both positive and negative terms or positive comma negative comma 0 terms. Okay, so we can compare and write the nature by using eigenvalues and also using the characteristic equation. When all the coefficients or the characteristic equation is having only the positive terms means it is positive definite. When a characteristic equation is having only negative terms means it is negative definite. When a characteristic equation is having both positive and 0 terms means it is positive semi-definite. When a characteristic equation is having negative terms and 0 term means it is negative semi-definite. When the characteristic equation is said to have both positive negative terms or positive term 0 term negative term means then they will be called as indefinite. This is finding nature by using characteristic equation, and we can also deduct the nature by seeing the eigenvalues. When we are having 3 eigenvalues and all the 3 are positive means positive definite, all the 3 are negative means negative definite, and we are having 2 positive 1 0 or 1 positive 2 0 means it is positive semi-definite. If we are having 1 negative 2 zeros or 2 negative 1 zeros means it is called as negative semi-definite. And if we are having the 1 positive 1 0 or negative or 2 positive or negative or 2 negative or 1 positive terms in eigenvalues means then they are called as indefinite. Okay, now how to directly find this from matrix, the nature using the matrix. So here we are having matrix A. Here we are having matrix A, and I shall write it here itself. We want to write a minus of main diagonal elements. We want to write the minus with something called as, first one is A11. So here A11 equal to 0. So it is 0. And after that we are considering, so first we are considering this, and after that we are considering this minor. After we are considering this minor, that is, this is called as d1. This is called as d1 equal to 0, and d2. This is not for me. This is not the meaning of diagonalization, but we are using a notation d1, d2. For diagonalization, we are using only d, whereas for finding nature, we are using d1, d2, d3. So d2 equal to 0, 1, 1, 0. It should include the main diagonal elements 0 and the 2 zeros. So it is minus 1, 0 minus 1 is minus 1, and d3. D3 is determinant, complete determinant. D3 is determinant of A. That is this whole thing. This whole thing. Okay. So first we are taking this alone, and next we are taking this alone, and for D3 we are taking this whole thing. In this whole thing. Okay. So we know that determinant is nothing but S3. Our S3 is, what is our determinant of A? Our S3, that is equal to 2. So since these D's D1, D2 and D3 is having both positive and negative terms, both positive and negative term, or positive, negative and 0 term, the nature can be called as indefinite. Here indefinite is nature of the quadratic equation. Indefinite is nature of the quadratic equation, or the nature of the eigenvalues, or nature of the matrix A, whatever it is. So we can use this technique when in the question they asked without reducing the matrix into, without reducing matrix, find the nature of the quadratic equation. If they ask or find nature of the matrix without reduction of, if they are asking like that, means we don't want to find diagonalized matrix, we don't want to find eigenvalues. We can simply reduce the matrix into we can simply reduce the quadratic equations into matrix, and after that we can easily find d1, d2 and d3. If all d's are positive, it is positive definite. If all d's are negative, it is negative definite. If the d's are positive and the zeros, means it is positive semi definite. If the d's are negative and zeros, means negative semi definite. If d's are both positive and negative, or positive, negative and 0, means they are called as indefinite. They are called as indefinite. I hope you all enjoyed this video, and in the next session we shall use this Casio calculator in efficient way to find some other operations in matrix. Okay. So before closing this video, let me check whether everything is correct or not, because it is a duty of every student or professor after completing a problem whether we have done everything in the right way or not. So I am checking here once again for a correction. Yeah, I have found some corrections here. So the corrections are here is root. Here is root everywhere. Here it is root everywhere. So we cannot write it as minus 2 by root 6. We cannot write it as minus 1 by root 3. Okay, it is 2 by root 6 only correct. So here everything is root. So we can sometimes the mistakes are unavoidable. Sometimes the mistakes are unavoidable, but we have to get the resultant diagonalized matrix in a right way. The resultant diagonal matrix in the right way. So if I actually multiply these terms without root means definitely I will not get this term. So I am advising my students, please don't multiply these three matrices in examination. These three matrices in examination. So you can simply write the eigenvalues in the diagonal and zeros in the remaining positions. That is what I have told in the session between our session. That is, so the diagonal matrix is always called as a triangular matrix. It can be upper triangular matrix or lower triangular matrix. So for a triangular matrix, the eigenvalues are nothing but the diagonal elements. It can be called in converse also. So the diagonal elements are nothing but its eigenvalues. So even though I have made mistakes, I have written the answer correctly. This is what I am expecting from all of the subscribers or students whoever is watching this video. So we can make mistakes. Sometimes mistakes are not available. Mistakes are not permitted, but sometimes mistakes are not avoidable. So even though if we make any mistakes here, okay, even though we make any mistakes here, we have to write the answer correctly to get correct. We get full mark. So I am always telling you to write. You can write without multiplication. We can write your answer without multiplication. Okay. So this is what I want to convey to you. So finally, now the problem is having no corrections. Everything is okay. A canonical form, everything is okay. So we can come to the conclusion that I hope this video will definitely use the initial learners who started learning matrix and determinants. So till your plus 2 you don't know what is mean by diagonalization, what is mean by canonical form, what is mean by quadratic form, and what is mean by reduction of matrix to canonical form, all those things, and nature of the quadratic form also. Here we can find nature of the quadratic form and everything. So now we have just stepped into higher level of mathematics. So definitely I hope this video will be useful for you, and if you like this video, kindly subscribe and also share this video so that others can also get the same benefit as you get. Okay, thank you for watching this video.